Hello everyone, and welcome to this introductory video to the series that I'm working on, where I reteach pre-calculus in what I think is a much more intuitive way. Like if I were to reteach myself pre-calculus, this is how I would do it. And so this introductory video is just to explain a few things about what to expect with this series, and a few notation things as well. So if you're good on all that, you can skip around to the other videos. And I don't have a proper name for this series yet, I'll figure that out. But right now I'm just going to call it PreCalculus Redone. Thanks for stopping by, because pre-calc is hard and sometimes very confusing. So whether you have some extra time over the summer before pre-calc, or whether you're cramming for your test tomorrow, I hope these videos offer some help and insight into the math that you struggle with. To help you guys out, I'll try to make every video independent of each other, so feel free to skip around the videos based on your needs. What's interesting about pre-calculus is that it's uniquely placed among all the classes you've already taken, and any classes you will take in the future, because it wraps up the entirety of all the math classes you've ever taken up until this point, as one final class before you move to the realm of calculus. Because calculus basically takes everything you've done so far, and then adds a new twist to it. So you need a strong understanding of everything previously to do well. And you'll notice in this list, I don't have pre-calculus, because it's really just algebra 3, which is just algebra 2, but a little more, and then trigonometry. So that's really all pre-calculus is. With this series, I really want to place a strong emphasis on an intuitive understanding of what's going on. So like, you can represent everything in pre-calc with a graph. And so I intend to do that a lot. With a lot of diagrams and some help from Desmos, I hope you'll be able to develop the intuition behind pre-calculus more easily. However, for this to work, you're going to need a basic understanding of what is going on, because here we understand why. To become better at pre-calc, you need to put in effort, as with anything. But for pre-calc, that can mean a lot of things, depending on what works for you. Maybe for you, you just need a ton of practice problems, or maybe you just need some really good notes. So hopefully the examples in my videos are diverse and difficult enough to show you the many cases we come across, and I hope the diagrams in Desmos can be a useful addition to any notes you take. I also highly encourage getting familiar with Desmos, and also making your own Desmos tools. So in this series, I'll make some Desmos tools for you guys to show what I'm trying to show you, but I encourage you to make your own. To make Desmos graphs, you have to understand what's going on. So in order to make them, you force yourself to learn how it all connects together. And one last thing before we start actually doing math. Showing work and notation. So up until this point, showing your work was kind of optional, kind of not. Like, you had to show something, but even if it didn't really make sense, it was fine as long as you showed something. But once I hit pre-calc, and once you hit pre-calc 2, showing work becomes very important. And more specifically, it's the exact steps you do, the process. And it's not your teacher trying to annoy you. It's proving that you got the right answer. That's how I see it. When you show your work, you're proving that you did the right steps for the right reasons to get a right answer. And that your source isn't trust me bro, it's actual logic. So that's why notation's important. And so here's a few things that I really want to go over with notation. So first is set notation. So as we see here, we have an equation, x squared equals 4. Now as we see, there are two solutions. That's -2 and +2. And so this is perfectly fine. However, the more technically official way to do it is to use curly braces around your solution, because it's a list of numbers, or a set. This isn't too important, it's just more formal. D&E versus no solution. So what happens when you come across issues like dividing by 0, or negative arguments in the log? When do you use D&E, which stands for does not exist, and when do you use no solution? And the difference really comes down to whether there's an equal sign. So is it an equation, or is it an expression? So let's do the equation first. So if we do some basic algebraic maneuvering, and multiply x to both sides, we get 2 equals 3. And additionally, x cannot equal 0. So 2 equals 3 cannot ever be true. No matter what we do with x, it's just not true. So this equation doesn't have a solution. There's no x value that would ever make 2 equal to 3. So we write no solution, because this is an equation, and we are trying to find a solution, but we found that there are none. I think some teachers say like doing that is okay or something, but no, please don't do that. You can write no solution. You can also write an empty set, because it's like you don't have any solutions, so your set of solutions is empty. I prefer writing no solution. It's 2 English words, but it's fine. It feels more formal. The important thing is you cannot end with nothing. You have to make a statement that there is no solution. Otherwise, your teacher will assume that you forgot to finish the problem. But you didn't forget. There's just no solution. So with an expression, there's no equal sign. This is a value. So if you think about it, let's say we had the expression e to the 3.5. That's an exponent. This is just a number, right? And it has a value. It exists. But with log base 3 of -5, this negative presents an issue. That just does not exist. That's not a number. We cannot evaluate this log. If you try plugging it into your calculator, it's going to throw an error because it does not exist. So it quite literally does not exist, Dini. You could also throw an equal sign on there. I do that sometimes, although technically just end off with Dini. Once again, don't leave it blank. You have to say that it does not exist, because if you don't, then your teacher will think that you forgot to answer. And you didn't. It just does not exist. So there are many ways to describe intervals. There are 2 big ones, and then there's a third one that comes in handy sometimes. So I'm going to really emphasize the first 2. We can use an inequality to describe this. Let's say we're using the variable x. X is less than or equal to -2. Because all these values are less than, and then because this is a closed circle, it can be equal to -2. Inequalities are very handy for algebra, so we'll get into that some other time. What's also handy is interval notation. So interval notation has start points and end points. So because we go off to the left forever to infinity, we start off with -infinity. And we use parentheses because it's infinity, doesn't have a value. Infinity is a concept. So we just throw parentheses on there. Then we do comma, and then we do our ending number. So in this case, -2. And because it's a closed circle, we use brackets to indicate that the -2 is part of this region. So what we have is, we have whether it's included or excluded, a start number, that comma indicates that we're going from the first number to the next, an end number, and then whether that's included or excluded. So we start at -infinity, and then we go to -2 and include -2. And that's interval notation. And it's a lot easier to write in some situations. In this case, it's about the same amount of effort, but in others, interval notation is better. So let's look at this region. So with inequalities, we can do the same thing. So x less than or equal to -2. In order to account for this region over here, we're going to need to write another inequality. X is greater than 3. And we use greater than, not or equal to, because it's an open circle. To join the 2 together, you have to write the word or, because x values can either be in the left region or the right region. This can very quickly get very clunky. So this is where interval notation comes in handy. So we'll start at -infinity, go to -2, include -2. Then what we'll do is we'll write the second region. We start at 3, but we exclude it because it's an open circle. Then we go to positive infinity. You don't have to write the plus. You can just write infinity. We go to infinity and exclude that. To join the 2 regions together, we throw a big U for union. We unite them. So that is much more concise than inequalities. This is our last one. This happens a bunch in pre-calc, which is why I included it. So to describe this with inequalities, it's a little weird. So I actually wouldn't do that. I would just go straight to interval notation. So we start at negative infinity. Then we go to -2, and we exclude -2, because this time it's an open circle. Then we union, open circle again, because we have to include this middle region now. Start at -2, but exclude it. We go to 3, exclude it, union, start at 3, then go to positive infinity, and exclude that. With inequalities, it would be really annoying. But we also have a third option, and that's called set builder notation. Now, you don't really use it too much, but it does exist, and it makes this process a little more concise. So you start with a bracket, and then x. So we have to say what type of number x is a part of. So you might remember that there are different sets of numbers. So there's real numbers, there's also integers, natural numbers. So in this case, x is any real number, because we have the full number line. It could be pi, 1.2, any of those numbers are on this region. So I'm going to start with all real numbers. And to say that x is part of all real numbers, we do it backwards 3, because it's a little curvy. And this basically just means x is an element of. You see the e there? Then we do a line to show that there are exceptions, because x is not all real numbers. X cannot be -2 and 3. That was just a few notation things that play a big role in pre-calculus, so stay tuned for the next video on absolute value.